Right. So we're starting in on number 3, and we'll go 3 to 10 today. The third one is the quadratic, the famous quadratic. Again, this is parent function, so nothing's been done to it, okay? When you do a quadratic, the parent quadratic here, your vertex happens at 0, 0. If you plug in 1, what do you get? What is 1 squared? 1. If you plug in -1, what do you get? 1, right? So it's this nice little parabola. How about if I plugged in 2? You'd get 4, right? I get this nice parabola that rounds out on the bottom here. Well, it should round out at the bottom here. OMG. What's the domain of this quadratic function? Yes. Is that hard for anybody? How about the range? 0. Who's miserable? Me? Oh, he sounds miserable.
Yeah,
0 to infinity. How about the end behavior? As x approaches positive infinity, what does y do? Positive infinity. That's right, exactly. Both ends go up, and that's exactly what that tells me. Nice. Is it continuous?
Yeah.
Yes, it does have continuity. It is continuous. What about symmetry? Does it show any type of symmetry? Even symmetry. Good job. If f of x is x squared, then if I do f of negative x, that is negative x squared, which is same thing that I started with. So it is even symmetry. Y'all good?
Yeah.
That's number 3. I told y'all this wouldn't be bad. Number 4. Number 4 is a square root graph. I hope you remember these from Algebra 2. If you think about a square root graph, what can never happen with a square root? Can't have negative where? Under the radical, okay? So if I start at 0, what's the square root of 0? 0. I can't plug in -1. I can only go forward from there. So what's the square root of 1? 1, right? So 1, 1. And so my graph, and I'll take this out to 4 since the square root of 4 is 2. So there's what it looks like, okay? It's not infinite on both ends. In behavior on this one's a little bit different. Actually, let's do domain and range first. What's the domain? Remember, I have a radical, so that's impacting my domain. What is it?
Negative or 0.
That's exactly right. How about the range? Same thing. It's the same thing. Now, in behavior is a little bit different because, and this is where things start to get a little bit sticky, but they're not bad. You can do it. I can't say as x approaches negative infinity because x doesn't go to negative infinity. What does x go to? 0. X goes to 0. It stops there. It is a point right there. So I say as x goes, is she okay? So as x goes to 0, what does y go to? 0. Look, this is 0, 0. It doesn't go any further, okay? So the left end of the graph in this case doesn't go to negative infinity. It just goes to 0. But the right side positive infinity. What does the graph do? It goes to positive infinity. Because it's creeping up. Even though it's creeping up slowly, it's still going up. The square root of 4 is 2. If I keep going down, the square root of 9 is 3. It's going to keep going up as I move down, just slowly going up. Is it continuous? It is continuous. Why is it continuous? What did I tell you to say every time? Yes, it is continuous because it is continuous for every value in the domain. That's exactly right. Okay. Let's see. Does this one show any type of symmetry? No. Yes. No symmetry. If you make x negative, so you were right the first time. Go with your gut. If f of x is the square root of x, if I do negative, right, this is an imaginary number, and I'm not graphing imaginaries, but regardless or not, that's no relationship there, so there is no symmetry. You can also look at the graph here and tell if you turned it upside down, it wouldn't look the same. If you reflected it over y again, it wouldn't be the same. All right, everybody good on that one? Yes, Miss McGee. Hello, Miss McGee. Okay, thank you, class. Okay, next one is a cubic. No, there's only 12 altogether. I was, but I'm not going to take y'all through 20. All right, the next one is a cubic. And I hope you're familiar with this graph. You should have seen at least... There might be 13 because I think I included cube root whenever it was in the book. So I think there's 13, not 12. All right, so if I plug in 0, what do you get? How about if you plug in 1? What's 1 to the third power? But negative 1. Negative 1, good, because negative times negative times a negative is a negative. So this graph looks like... Now, this is not just a line, okay? Because if I plugged in 2, what's 2 to the third? 2 times 2 times 2. 8. Same thing, negative 2 is negative 8. So what's going to happen is 1. All right, it's going to be way up here. Okay? And way down here. What I'm trying to show you is that when you graph this, it does this. That's exactly right. Okay? So, what's the domain here? Good job. How about the range? No infinity to what?
No.
Bottoms up. Up to infinity. Yeah. Because it keeps going up. Somebody said 0. Is it continuous? Why? It's continuous for every value in the domain. Does it show symmetry? What kind? Oh, I hear both. Let's see. If f of x is x cubed, then f of negative x cubed, which would be negative x cubed. So it's an odd function. Exactly opposite is odd. The exponent, yes, yes. How about in behavior? That's exactly right. How about the other end? Perfect. Everybody good? That is the cubic. With a K.
When you get to your third block class, tell them that you're listening.
Let's do number 6. This is, if we did cubic, I wanted to show you cube root. This one's not in your book, so this is a freebie for you. There you go. You're welcome. Yeah.
Every single one.
They're pretty easy to come up with if you don't memorize them, though. They're pretty easy to plug in 0, 1, and -1 and find the graph. And then you can do the analysis. I mean, you technically could. All right. Let's see. If I go with 0, the cube root of 0 is... That's where y'all say 0.
0.
The cube root of 1 is? 1. The cube root of -1 is?
-1.
So you might say, well, Miss McGee, that looks just like the other graph. But if I keep going, it's going to smooth out like a radical graph. Because if I went out, what would be the next one? 8. If I did 8, the cube root of 8 is what? What times itself 3 times gives you 8? No. You're doing to the third power. I'm asking for the third root. What? It's 2. What do you multiply 3 times to get 8? And it's 2. So it's going to be like here. You see what I'm saying?
What point is that? 8?
Yeah. -8 would be -2. So this graph does this, and it looks like it smooths out, but it's still creeping down ever so slightly. Okay, that's a cube root graph. Looking at this, what is the domain? Yes. How about the range? Same thing. Ditto. I like that. Is it continuous? Why? Where are you at, Jerome, with a G? It's continuous for every value in the domain. Okay. Yeah. You said it a little backwards, but that's okay. I give you credit for it. I got you. I knew what you meant. All right, so yes, it's continuous. How about in behavior? I'm going to need you to be a little more excited about it. This is good
As
stuff.
X goes to infinity.
Not louder. Excited does not mean louder. What am I missing? Symmetry. Does it have symmetry? What kind? Odd symmetry. It's odd symmetry. If you plug a -x in there, the cubed root of -x, you can take the negative out on the outside since it's an odd root, and it looks exactly the opposite, so it's odd. All right, moving right along. Are y'all bored? Don't answer that. Let's do number 7.
How many of these are we doing?
12.
13.
13.
17 million.
I know y'all are so excited about this.
Do we have homework tonight?
See.
How much homework?
All right, number 7. We're going to get to one. Number 8 is one y'all haven't seen before. All right, this is a reciprocal function, 1/8. We have graphed the crap out of these. Okay. This is where we have horizontal and vertical asymptotes. We have them at 0 and 0. So we have, remember we set the bottom equal for our horizontal asymptote? Vertical asymptote, I mean. I'm thinking about the horizontal asymptotes in a minute. All right, so x equals 0. Vertical asymptote. Horizontal asymptote, it is bottom heavy. Y equals 0 is my horizontal asymptote. If I plug in a couple points on either side of the asymptote, we'll go 1, 2, we'll go -1, -2. 1 over 1 is, thank you. I'm looking at this equation and plugging in. 1 over 2, -1 and -1/2. Okay, just plugging into that equation so that you can see the graph here. So I have 1, 1, and I have 2, 1/2. So it comes around and hugs, and hugs. And then -1, -1, -2, -1/2, and it hugs, and it hugs. What is the domain?
-infinity.
0, 0,
Yes.
U,
Yes.
0,
Yes.
infinity.
Absolutely. Again, this is the parent function. We'll be doing things to the parent function to move it, stretch it, shrink it, flip it, slide it. No. How about the range? It's the same. You're exactly right. It's the same bottom up or left or right. All right, everybody okay? Is it continuous? It actually is. Why? It's in the, that's exactly right. If you say it's not, that's exactly right. Y'all, that's great. 0 is not included in my domain. So because the only discontinuity happens at 0, I can't count that. So other than 0, is it continuous? Yes. So yes, the function is continuous because it is continuous for every point in the domain. Okay. If the domain was -infinity to infinity, then no, this would not be continuous. Right? Y'all with me? Okay. What's the end behavior look like?
okay.
What does y approach? The right side. Far right. The bigger x gets, what is the graph doing?
Oh.
It's approaching that asymptote. It's getting closer and closer to that asymptote. Do you see that? Remember we talked about that when there's that horizontal asymptote it's going towards? How about as x approaches -infinity? It's 0 again. It's going to 0 from both sides. All right, here we go with some new stuff. Yeah. I got nothing better. Oh man, I think I took cuboid out. I'm looking at the wrong thing. It's okay. I did. Sorry. All right, next one. Number 8. You should have seen this at some point in geometry. When you were doing probably right triangles. You saw the function sine. Sine, cosine, and tangent. You probably remember SOHCAHTOA with right triangles, right? I hope I'm not speaking like a whole other language, like I'm showing you something you've never ever seen in your whole entire life. It is. And so we'll do a lot with trig functions in here. So this is our, yes.
No, I was probably going to prove this. And I know you can't do none of that without a camera. Unless you
Wait, what? Hold on. Let me pause again. Now, listen, we're not going to get into, we will. We're going to get into a unit circle real soon. we're not going to get into why it is what it is just yet. Right now, I just want you to know what the points are. They're going to look really weird because we're going to be in what we call radians instead of in degrees, okay? So our numbers are going to look a little crazy. They're going to have pies and stuff like that in it, but that is okay, all right? These functions are different. They never go above 1 or negative 1, okay? And some important points here. And again, your calculator, I know Jerome with a G is wanting to use his calculator for this, but unless you're in radians, I don't think it's going to give it to you quite the way we want it. All right, the sign of 0 is 0 every time. Okay? Every time it's 0. Then what we're going to do is we're going to go by half pies. Okay? We're going to say this is half of a pie. This is a pie. This is one, yes, I do expect you to know this. This is 1.5 pi, so 3 pi over 2. Wait until you get your whole unit circle you have to learn.
What?
Wait, what happened if you
I was just mad.
You drop out failing.
That's an option.
This would be 2 pi. We're going to do the same thing on the other end. We're 3 pi over 2. That's 1.5 pies. That's 3 over 2 times pi.
That's like 1.5 pi.
Absolutely not.
It's gonna be on our test.
Yes. Shh. I haven't even asked y'all to do anything.
This whole thing is messed up.
And you put power with a fraction.
But
and you got
listen.
numbers next to power with a
Listen.
fraction.
Woo, y'all might should have taken problem stats because this is the backbone of pre-cal right here.
They told me this was easier than problem stats.
Right now I'm telling you the points, okay? Right now I am telling you the points. This would be just like if this was 1, this is 1 pi, this is a half of pi, okay? I'm just get. Oh, I skipped one, I'm sorry. Y'all started whining so much you got me distracted. Lord, I hadn't even done anything yet. Negative pi, sorry, negative 3 pi over 2. And the nice thing about trig functions is they are very repetitive. Once you get them going, they continue with the same pattern, okay? So I start at 0, 0. At pi over 2, the sign of pi over 2 is 1.
Always.
Always. The sign of pi is 0. The sign of 3 pi over 2 is negative 1. I'll show you why. We're going to do a unit circle, and we'll actually derive the unit circle, and you'll see why. We'll get into that extensively. Okay? And then the sign of 2 pi, can you guess what it might be?
0.
0. Do you see what it's doing? Up 0, down 0. Up. Remember I told you? That's exactly what it's going to do. You may have heard about a sine wave before. It looks like a wave. Okay, this side's going to do the same thing. Down, up, 1, down. Okay? I'm not asking you to do a lot with this other than to recognize how to graph it. Okay? So what it's going to look like, this one's kind of stretched out because my units are not very well, but I just kept with the pattern. That's going to be the pattern infinitely forever. Okay. So I plotted the ones on the right side.
Yeah, I know. These are just part of the thing.
Okay. So looking at this now. Okay. What is the domain of this function? Negative infinity to infinity. What is the range? And be careful, look at the graph here. Yes. It never goes below -1, and it never goes above +1.
Why?
It's never defined there. When we do our unit circle, and we get into all that, but unit circle's tough when you first know it, but it'll make a little more sense. All right. Right now, I just want you to know those points. If you can get the first cycle, okay, like the first 0 up, 0 down, 0, you can plot all the rest of the points, okay? You're just going by half pies whenever you do it, okay? I have this in a printout for y'all too. All right. Now, we got domain, we got range. Is it continuous? Yes. It is continuous for a point. I do not have to lift my pencil up in order to do that.
No.
What's the end behavior?
Everything goes to
This is difficult.
the range is always -1 to 1, right?
Okay. The range is always -1 to 1. Here's what's happening. Look at the end. Tell me, because it's oscillating between two numbers. What's it oscillating between? -1 and 1. So as x goes to positive infinity, y, I'm going to literally say oscillates between, you can, -1 and 1. Everything is different when we start getting into trig functions. Rotates between. Think about an oscillating fan, how it goes here, and then here, and then here, and then here. So it means it just goes between those two consistently. The further you go, it's just steady going. -1, 1, -1, 1, -1, 1. And I'm going to say it does the same. I'm going to make this one sentence. I'm going to say as x approaches positive or negative infinity, it's doing the same thing on either end, okay? It's going, oscillating between the two values. Is it symmetric? I hear yes and I hear no.
I don't really know.
I would say yes.
Is it symmetric about the y-axis? If you put a mirror there, would it look exactly the same on either side? No. If you flipped it upside down, would it look the same? 180 degrees?
No.
You don't think it would?
No.
It would. It would. If you, 180 degrees, odd, not even odd.
But I said, yeah, it would look like that. You said you flipped it 180.
Oh, I thought you were saying yes to the symmetry. I mean, the y-axis symmetry. I'm sorry, Jerome with a G. I apologize. Yes, yes.
If you're really sorry, you make it.
It is odd. Okay. Let's do cosine then. I'm going to have to... All right, cosine, number 9. This is going to be the same kind of thing. Okay. I'm going to set up my graph. I'm going to go by half pies. Pi over 2. You're going to see that these are so similar, in fact, that the only thing they've done is shifted over, essentially. Negative pi, negative 3 pi over 2, negative 2 pi, 1 to 1. Your points for this, the cosine of 0, what was the sine of 0? What was the sine of 0? Sine of 0 was 0. The cosine of 0 is 1. But listen, the nice thing about these is if you can figure out, and you can type on your calculator cosine 0, and it's going to give you 1. And if you type sine 0, it's going to give you 0. Now, once you get past that and into the radians here, the pi's over 2's and all, it's going to give you a big long decimal, and you're not going to know what to do with it. But if you know a starting point with these, you know they always are up 0, down 0, up 0, down 0. They're the same pattern every single time. Both of them are. So if you know whether to start here or here, you should be able to get the rest of the graph, at least by points. Okay? You can. The cosine of pi over 2. And if you start putting cosine pi over 2 in your calculator, you would need to make sure that your calculator was set to radians and not degrees, and we hadn't quite got to that. All right, the cosine of pi over 2, what do you think it is? 0. What do you think the cosine of pi is? -1. See how if you know what to start with, you can figure out the rest of them? What do you think the cosine of 3 pi over 2 might be? And how about the cosine of 2 pi? 1. Same thing here again. Down, down, 0, up. So I've got this nice curve. Come on. I know that this is new and foreign looking to you, as it should be. You haven't done this before. It's the first time you've ever seen the graph of a sine or a cosine function. And it is a function because it passes the vertical line test, right? What's your domain here? Yep. How about your range? Domain and range are exactly the same for sine and cosine. We're not going to get into tangent just yet. We'll hold off on that. Is it continuous? Yes, it is continuous. Does it show symmetry? What type? Even. Why? If you hold a mirror in the middle, it's the same on either side. Okay? And all it's done is slid over is all it's done, and that's changed the whole symmetry of the whole function. Okay? The end behavior is exactly the same as it was with sine, so I'm not going to write that for the sake of time, so we can get through. The end behavior is the same for both of them. All right, let's get out of trig for just a minute and let's do these last 4. You know what I think I'm going to